So, last class I have discussed that how you will get the shear force, bending moment, settlement and slope when a infinite beam is subjected to a concentrated load. Okay. Now, today I will discuss the how the infinite beam, if the infinite beam is subjected to a concentrated moment, then how I will get the all these equations. So, quickly I will discuss that, because this moment and the this concentrated load, these are very important. These two, by using these two cases equation, I will get the other equations also for different conditions like infinite, like finite beam, semi infinite beam cases. So, suppose this is a infinite beam which is a concentrated moment m0, or m0 is acting. So, this is x and this is also infinite beam. Okay. So, now this case can be drawn or can be represented in this form also, because this is a concentrated force P and this is a concentrated force P whose distance is A. So, I can write, say suppose this is your O point, I can write that if A tends to 0, then P A is tends to m 0. Okay. So, that means I am writing in this, or I am representing this moment into this form. So, now what will be the deformation due to this condition? So, deformation W will be, because this is, suppose now it is an infinite beam. So, I am considering this, the where this this lower direction force is acting, then that is equal to or so, or I can write that this distance of this point at any point is say this is the P point, and the distance from this P point to another P concentrated load point is A, but one case it is acting downward direction, another case it is acting upward direction. Okay. So, now suppose we have a point whose distance from this downward load acting force is x, and I want to determine the deflection at this point. So, deflection at this point, this point is say A. So, deflection at A point will be what? So, deflection equation, you know, the deflection equation for a concentrated load is P W P lambda by 2k into A lambda x. Okay, that is the equation. So, here one point is P lambda by 2k and this is A lambda x, and upward acting concentrated load is considered as positive, downward acting concentrated load is considered as positive. So, this is positive and upward acting is considered as negative. So, moment I have given, what is the sign convention, that in the moment the clockwise moment in left side is positive, whereas the anti-clockwise moment in your right side is considered positive. Okay. And the upward acting concentrated force is negative and downward acting concentrated force is positive. Okay. And remember that all the equation that will be derived in this way, it is for valid for clockwise movement. So, this is for clockwise movement. So, this is for clockwise moment. And then, so that means here it is upward acting, so it will be minus. So, p lambda by 2k, now this will be a lambda x plus a, because that is the distance of x plus a. So, I can write this equation as minus p a lambda by 2k. So, if I take basically p lambda by 2k, then this will be minus I have taken a lambda x plus a minus a lambda x, and I have taken a, so we have to divide a. So, this is the equation. Again, these equations are valid for x equal to 0, that means for the right side. So, now I can write that for a lambda x plus a minus a lambda x plus a lambda x divided by a, if a tends to 0, that means this will be equal to d dx into a lambda x, d dA into a lambda x, and a lambda x given e to the power minus lambda x cos lambda x plus sin lambda x. So, if you differentiate that, you will get this is equal to minus 2 lambda b lambda x. So, this a lambda is b lambda x, c lambda x, d lambda x, all are given. So, this is b lambda x. So, finally, I can write that your w at any point, because initially I have taken one point, now it is any point, will be equal to minus p a lambda divided by 2k into minus 2 lambda b lambda x. Now, for p a, this is a p a is given, a tends to 0, this will be equal to m 0, I mentioned. So, this will be your 2 will cancel out, this will be m 0 lambda square divided by k b lambda x. So, this is the equation of deflection for the concentrated clockwise moment in right side. Similarly, I can write the slope equation, and that is m 0 lambda cube divided by k by c lambda x. Bending moment is equal to m 0 by 2 d lambda x. Shear force is equal to minus m 0 by 2 lambda a lambda x. So, these are equations for concentrated clockwise moment. So, you can get these equations as I have discussed in concentrated load case. Thus, if you do dw dx, you will get the slope, then the d square w dx square moment, then dm by dx is for the shear force, like this. Now, again, if it is all these equations are valid for x equal to greater than 0. Now, in this case, that your w x greater than 0 will be equal to minus w x less than 0. That means, if it is on other side, now previous case concentrated load case, the w and bending moment, slope at bending moment, there was no change. But now, there will be opposite sign in case of deflection and the bending moment, because in previously in deflection and bending moment there was no change. Now, in deflection and bending moment there will be opposite sign, but for the slope and the shear force they will remain same. So, now this is the case, and for the slope x greater than 0, this will be slope x less than 0. Bending moment x greater than 0, that will be equal to minus m less than 0, and shear force x greater than 0 will be equal to shear force x less than 0. So, now these are very important. So, that is why I have discussed the bending moment and concentrated force. So, concentrated force upward direction and bending moment in clockwise direction. Now, if it is opposite, suppose concentrated force is acting in concentrated force in downward direction I have given, and the bending moment is given for clockwise moment. Now, if it is in opposite, concentrated moment load is acting in upward direction and the bending moment is acting in anti-clockwise direction. Okay. Then all the equation you have to put minus sign. That means, in such case W will be equal to minus m0 del square by k b lambda x, if it is x equal to greater than 0. Now, accordingly, for x equal to less than 0, then you have to modify your equations like the cases I have explained. Okay. So, only if the loading is acting in upward direction, concentrated load, or moment is acting in anti-clockwise direction. So, in case of P or P0, it will be minus P or P0, or in case of M0, it will be minus M0. That is it. Okay. Now, I will give idea if it is a uniformly distributed load. Okay, so uniformly distributed load case also you can calculate. Suppose if you have a uniformly distributed load here. Now, if you have point A and B and your point of interest is C at this point, which is at a distance of say A from the A point and B from the B point. Okay. And this is uniformly distributed load is Q, and you have to take a small segment of dx. Okay. Now, that dx is because of that dx. So, the concentrated force is acting because of this dx, there will be a concentrated force and that will be q into dx. So, that means this UDL is considered as a number of concentrated force of q into dx, because they have taken the number of dx elements. So, that means number of q into dx is acting over there. So, all the n number of concentrated load is acting over this UDL. Now, you know that for the concentrated load for this small segment, I will get the del W, this delta in W, the small deflection, and that will be equal to P lambda by 2k, and here lambda by 2k into A lambda x at any point due to this small concentrated load q into dx. This is the equation. Now, this P we have to replace by q into dx, q into dx. Okay. So, now if I want to get the similarly the deflection at C point, if I want to get the deflection at C point, W at C point, then what I have to do the integration. So, there is the two region, one from 0 to B, another from 0 to A, and as I mentioned, for deflection whether it is the left side or the right side does not matter, all will be we have to add them, and so there is a number of n number of concentrated load. So, due to this n number of concentrated load, I will get the deflection at C point. So, in such case all the contribution you have to add if there is n number of concentrated loads. So, you have to add all the settlement due to this all the particular concentrated load. For example, in C, in the C point there will be a settlement due to n number of concentrated load, because there is say concentrated load 1, 2, 3. So, due to 1 there will be a settlement at C, due to 2 there will be a settlement of C, due to n there will be a settlement of C. So, we have to add those settlement, then I will get the settlement at C point. So, that means we have to integrate that. So, this is the P lambda, or this is the P is replaced by Q dx. So, this is the Q by 2k, then integration 0 to A, and then A lambda x dx, then plus integration 0 to B A lambda x dx. So, this A lambda x, you know that Q lambda by 2k, this will be 0 to A. Now, A lambda x is e to the power minus lambda x cos lambda x plus sin lambda x. So, that is dx plus 0 to B. Now, this is whole third bracket 0 to B e to the power minus lambda x cos lambda x plus sin lambda x, this is dx, then whole third bracket. So, after doing this, finally, I will get the equation for the deflection at point C, or deflection at point C. So, that deflection at point C will be Q by 2k 2 minus d lambda A minus d lambda B, where A and B are the distance from that point C to the edge of the loading. Okay. Similarly, I will get the theta also. The theta also similar way I can calculate. So, I am giving the final expression, that is Q lambda by 2k A lambda A minus A lambda B, and the bending moment at C, Q at C, slope at C, that is Q by 4 lambda square B lambda x plus B lambda A plus B lambda B, and the shear force at C is equal to Q by 4 lambda C lambda A minus C lambda B. So, these are the equations for the UDL. Okay. Now, there is maybe this C point will be the outside of or the left side of the loading, C point can be right side of the loading. So, in such case you have to take the integration accordingly, and when you do this integration, put this value, remember that for deflection the left side it will be the minus sign, and for the deflection and the moment there will be no change, but for the shear force and the slope there will be minus sign when you do the integration for concentrated load. Remember that I have discussed, and for the moment the deflection and moment will change if it is in the left side, and the other slope and shear force will remain same. So, depending upon the position of your point of interest, now the point of interest is at within the loaded region. So, I have derived like this. If the point of interest may be your left side of the load, it may be the right side of the load, that means outside of the loading, either it can be left side or it can be right side. So, according to that you have to derive the equation. And another thing, in this equation you have taken A and B. Suppose if your A is equal to 0 and B is equal to your L, if A is equal to 0, B is equal to L, then it is at point A. So, at point A your A is equal to 0, B is equal to L, and for point B your B is equal to 0, A is equal to L. So, if you put these values, you will get the deflection and the other quantity at the edges of the loading also. So, this is the cases for different loading conditions, and now I will go for the semi infinite beam, and then I will give the idea how we will go for the finite beam also by using the same concept. So, now this is the semi infinite beam. And remember that here I have given the only concentrated load and moment and then the UDL, but there can be other loading option also. That means if there is a triangular loading, then also you can get the deflection, bending moment and all other parameters for infinite beam. But now the semi-infinite beam, suppose in there are three cases can be considered. One is your free end beam, then the next can be your hinged end beam, then that can be your fixed end beam. So, that means this is a free end beam, hinged end beam and fixed end beam. So, I am discussing the free end beam. So, similarly you can get for hinged end and the fixed end beam. So, free end beam I am discussing. So, this is the free end beam. So, actually this side is infinite, but this side is it's finite. That means there is a free end, okay, at point A, say. So, there is an end condition, it is not infinite, and there is a load is acting, say P, at a distance of say A from this free end. So, here what to do, that the idea is that how you can solve this problem, that we have to apply the boundary condition as the free end. What is the boundary condition as the free end? Now, for free end beam, your bending moment will be 0, bending moment at A will be 0, and bending shear force at A will also be 0. Okay, because this is the boundary condition for this free end beam, because there is one end is free. So, this is the boundary condition, that M A is equal to 0, Q A is equal to 0. Now, what we will consider now, that we will now consider this beam is an infinite beam. Okay. So, first step we will consider that this beam is infinite beam, and by using the infinite beam concept, I will determine what is the moment and shear force will develop at point A. Okay. So, now if I consider, if we consider beam as infinite beam, then the moment at point A due to this point load will be equal to P 4 lambda C lambda x, because this is the moment at point A due to this point load, and the shear force at point A due to this point load, that will be minus, because actual condition is minus P 0 divided by 2 d lambda x. But remember that now your point of interest is A, and which is left side to the load. So, bending moment there will be no change, but the shear force this will be positive, because this is negative, this will be positive. So, that means you will calculate this bending moment and the shear force at point A. So, now because of this, as we have considered this beam is now infinite, and because of this point load there will be a bending moment and shear force at point A, but actually this is not an infinite beam, it is a semi-infinite beam. So, we have to apply a counter moment and shear force, so that the net bending moment and shear force at point A will be 0, because that is the boundary condition. So, that means we have to because of this P, as we consider this is an infinite beam, there will be a moment and the shear force, but actually at that point the moment and shear force will be 0, because as per the boundary condition. So that means we have to provide a counter force and the moment such that the net moment at this point will be 0 and the shear force, net shear force at this point will be 0. So then it will be a semi infinite beam with free end, and free end boundary condition will also be satisfied. So that means we have to apply a force P0 and the moment M0 such that the net force and the shear force and the moment will be 0 for this particular case. So this P0 and M0, these are called end conditioning moment. Or end conditioning forces. So one is moment and the shear force or the force, one is moment and this concentrated force, but these are called end conditioning forces. So these P0, M0 I will call end conditioning forces, because one is moment but another is concentrated load. So now finally if I write that at this point bending moment should be 0. So finally I can write that MA, that is the moment due to point P, and the moment, because we have now applied a concentrated load P0 and a moment M0. So due to this concentrated load P0 there will be a moment at this point, and due to this concentrated moment there will be a moment at this point. So that means there will be 3 moments. What are the 3 moments? Now we have to make this bending moment and net bending moment and shear force 0, we have applied a concentrated force Pu0 and we have applied a concentrated moment M0. So at a point there will be moment due to 3 forces. One is P due to P, one is due to P0 and one is due to M0. So the moment due to P is Pa, which expression I have given. So moment due to P0 will be equal to P0 by 4 lambda, because the your concentrated moment due to concentrated load, I can write this equation that the W due to concentrated load is P lambda by 2K into A lambda x, slope is minus P lambda square by K into B lambda x. Now M is equal to P by 4 lambda C lambda x, shear force is equal to minus P by 2 D lambda x. This is due to the concentrated load, and due to the concentrated moment your W is equal to M0 lambda square by K into B lambda x, then theta is equal to M0 lambda cube divided by K C lambda x, then bending moment is M0 divided by 2 D lambda x, then this is Q minus M0 by 2 lambda into A lambda x. So these are the 4 cases, because these I have derived. So you should remember these equations. These are very important. So all the semi-infinite and infinite cases, these equations will be used. So but for that means the moment due to concentrated load P0 will be P by 4 lambda C lambda x. Now this is your point of interest is this one. So always remember your x will be the point of interest. X equal to 0 will be point of interest. So now here point of interest, where your this is x equal to 0, it is, so x will start from here. So your x is starting from here, at this point x equal to 0. So at this point x equal to a. So that means this particular case your point of interest is x equal to 0. Not only the always point of interest will be x equal to 0, no, that depends at where you are determining your value, but for this particular case your point of interest x equal to 0. So at x equal to 0 means c lambda x will be 1, because c lambda x is cos lambda x minus sin lambda x. So sin 0 is 0, cos lambda x, that is 1. So this is equal to 0. So now if x equal to 0, always remember that a lambda x equal to 1, b lambda x equal to 0, c lambda x equal to 1, d lambda x equal to 1, if your x equal to 0. Always remember that. So that means here this will be p0 by 4 lambda, and due to this concentrated moment, the moment will be your m0 by 2, again d lambda x equal to 1. So this will be m0 by 2, and that will be equal to 0 as per the boundary condition. Similarly, for the shear force also, I should write that your QA is the shear force due to the P, then the shear force due to this concentrated load P0 will be minus P0 by 2, because d lambda x will be 1, this will be P0 by 2. Then for this moment the shear force will be minus m0 by 2 into lambda, as a lambda x will be 1. So this will be minus m0 lambda by 2, that is will also be equal to 0 as per the boundary condition. So now after solving, so I will get that n conditioning force P0 will be 4 lambda ma plus qa, and m0 will be equal to minus 2 by lambda 2 lambda ma by plus qa. So ma and qa I will get from these equation. From these equation, ma and qa equation is given. So and this is basically, I should specifically write this is lambda a, because the distance is a. This one is also I can write specifically, this is equal to a, because the distance is a. So I will get these equation from ma and qa by using these two equation, and this is the end conditioning force. So that means this much of P0 and M0 we have to apply to make net bending moment and shear force will be 0. So this way, so that means now if I want to determine any deflection at any point, so now this is the case. So there will be a M0, a P0, M0, and there will be a P. So at any distance from this point x, I can determine the deflection, bending moment, shear force, because now we have 3 loading conditions and we have to add or subtract them depending upon its position and the values that or the equation that is given. Okay. So in the next class, what I will solve one particular problem for this semi-infinite beam, and then I will give you idea how you can use this concept for finite beam also. Then I will go for the beams on 2 parameter model, and then I will discuss about, this is the closed form solution I am talking about, and then I will discuss how this beam problem can be solved by using finite difference technique. Thank you.